Okay, so I'll just give a quick recap because some people might not have been there. So what I just discussed very quickly. Uh, uh, yeah, so essentially, so the idea was to motivate why we study SYK type models in condensed matter systems, and that motivation came from, of course, this long-standing quest to understand many materials, but prime examples being this kind of high temperature superconducting materials, cuprates, where you see this kind of strange metal phases, and then there are different ways of characterizing it through transport, sort of unconventional transport properties, temperature dependence, and then so the way that you also look at it from the view of spectroscopy or like Green's functions or spectral function is by looking into this, let's say the single particle Green's function, and then asking whether at very low energies, omega going to 0, whether sort of the bare part dominates or the part that comes from interaction, the self energy correction dominates. And that kind of, if you have a gapless system with some power law dependence of self energy, then this power law, whether this power law is weaker than the omega or stronger than the omega at omega going to 0, that essentially defines this dichotomy between Fermi liquid and non-Fermi liquid for the purpose of this talk. Okay. So that for us will be this definition of no well-defined quasi-particles. So I should say more Landau quasi-particles. Of course, you could have systems where you don't, a fermionic system, you don't have any fermionic quasi-particle, but you can have bosonic quasi-particle, for example, in Luttinger liquid. Okay. So those are still systems with quasi-particles, but we are just not looking into the right quantity. Okay, so now, so the main motivation was to sort of go beyond this conventional probes and then ask that can you sort of have more broader distinctions between non-Fermi liquids and Fermi liquids, which doesn't require you to choose, let's say, particular bases or particular types of fermionic or bosonic quasi-particles, but rather define it more generally. So transport is of course one such quantity, but then so the more broader way, maybe if you ask that can you characterize the states using thermalization, okay, or the rate of thermalization, and related to that in this SYK type of model you get this many body chaos, which I discussed little bit. I defined this OTOC, I'll come back to this later. So that's and then I went into looking into this very standard thing about OTOC. So that, and then the main thing I was trying to do is to warm up about looking into this SYK using a much simpler problem, which in fact you can solve very easily for very large system in computer, because it's a non-interacting system, which is basically a quadratic problem. The nice thing about this quadratic problem, so it's a infinite range model where all-to-all connectivity. So of course you can solve it in computer, but you can also solve it in this large n limit. Okay, and in the large n limit, using this, I tried to show the self-averaging. That is, so of course, typically when you do this large n theory, we do the disorder averaging. But in this model, without doing disorder averaging, you can show that how the same equations come up. Okay, so that was the main idea of this, looking into this. And I defined few quantities earlier, and then just to remind you, sort of the main contrast with the SYK, which I am going to discuss, is that so if you look into if you solve this problem, this non-interacting problem, then what you will find that you're near the ground state, the many body level spacing essentially is determined by the single particle level spacing, because essentially the way you create excitation in these systems are additive. So you can just add one excitations, and that gives the change of the many body energy. But this is very unlikely, this is quite unlike the SYK model, as we'll discuss, that the many body level spacing will be completely different from this particular thing. And we'll also contrast some of these other things, which is the many body density of states, how it varies with energy. Okay. So I also showed some numerical results of this earlier. Okay, so now let me come to this SYK model. So first sort of 45 minutes or so, I'll try to just work out this large n theory for the SYK model on the board. So let me go to there. So any question from the earlier lecture? Okay. Okay, so let me first again try to tell. So essentially, as I discussed through these slides, that effectively in this model, in the Largen limit, you get this saddle point equations, Largen saddle point equations, which effectively one equation is just the Schwinger-Dyson equation. That the main simplicity of the SYK model comes because the self energy in this limit, in the limit of Largen and disorder averaging, is exactly given by these Mellon diagrams. Okay? And so of course these diagrams still in all orders in this set of diagrams. So the lines that appear, the Green's function line that appears in the diagrams are the full Green's function. So you have to solve it self-consistently. And I actually discussed also some numerical methods to solve this self-consistency. Okay, so at least let's sketch the numerical methods. So now I'm going to discuss the low energy solutions of the same saddle point equations. Okay. Okay, so let me okay, so I'm defining the SYK model, as I said, this complex SYK model with a chemical potential mu. So the chemical potential I'm just putting in the Hamiltonian, but you can just think of this as a tuning parameter. So by tuning it, of course, if you fix the number of particles, then it does nothing because it's just add to this. But ultimately, we are going to think about a thermal ensemble with a grand canonical ensemble. So there you can tune this to tune the number of particles. Okay. So that's why you have added this. If you are just looking into a fixed number of particles, then it doesn't do anything. So again, so you can do this construction diagrammatically, which I will not discuss in detail. So just like in the random matrix case, I did it diagrammatically. So I can just sketch the few steps of this diagrammatic derivation, which will give you the same results that was shown earlier on the slides. So again, the way you do it in this model is you treat, so you expand again in this quantity Jij, So if you remember for the random matrix model, I did the perturbations using Tij, the hopping. So in this case, I will do this perturbation using this Jij. Okay. So again, I am doing with the bare Green's function, which is given by this. And so the vertex that you have here has 4 legs, of course, like this. So I can write, and then here again, so there is a disorder line, which is this Jij, and you have to remember that this disorder is again drawn from a Gaussian distribution. Okay, and it's uncorrelated between different this IJKL set. Okay. So again, you can try to draw this the Green's functions. So only the on-site Green's functions will focus on, because you can again show that this is the only Green's functions that will stay in the Largen limit. So essentially, all other Green's functions like this will be down by factor of 1/n. Okay. So you try to expand this, and just like in the earlier case, you'll have the initial bare diagram, and then so the first non-vanishing diagram that you can draw, you have to bring 2 vertices, because remember that you have to also contract this Jij, right? So only a non-zero average is Jij with J star Ijk, this average, okay, where these indices has to be same. So this is the only non-zero diagram that you can draw up to the lowest order in J. So then, and again, I am only drawing the one particle irreducible diagrams here, because ultimately I am just going to take out the self energy. So you can now draw the other diagrams. The next order you can have these vertices. And so this one, again, so you can just see how many ways you can connect these things. I just wrote it so that I can draw it quickly. Okay, so this is one thing you can draw, and this one again the disorder is contracted, this is non-zero. But that same order you can draw this other diagram. Yeah, thanks. Yes. Sorry, you mean you averaged it to connect the small circle to the large circle. Right. Wouldn't I instead average two vertices to the left and two vertices to the right? No, no, that no. So the thing is that no. So that's what I'm going to draw here. Okay. So no. So the thing is that you have to still, because you have only this on-site Green's functions, right? So whenever you are contracting the disorder line, right? So those the fermionic line has to be also be contracted with the same thing, because you don't have any ij, right? So it doesn't connect to I. It cannot connect I to a not equal to j. I mean, so I not equal to j, it will not connect, right? So that's why you have to also contract the same fermionic line. Yeah. So I can't really do this. Okay. Yeah. I mean, you can probably do this where everything will be I or something like that. But that's like, I mean, that I'm not keeping. I mean, I'm saying these are essentially, I'm not keeping things. I mean, yeah, those are anyway zero, because you can't have I equal to j. I mean, yeah. No, that argument I'm giving now. But the question was that whether you can do the disorder averaging like that, but like whether you can do the disorder contraction between these two vertices. Okay. Yeah. 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 Right. Yeah. Yeah. Right. Yes, I'll say. Yeah, I'm saying. Yeah, so first of all of them cannot be I, because there is some anti-symmetry of these numbers. Okay, right? So you can't have this. We can of course have two indices same here and here, but yeah, so that is already included in this contraction. Yes. Okay, so you can try to draw it, and I did it bit quickly, so but you can check whether, I mean, you can, yeah, just try to contract it different ways, see it gives non-zero contribution in the large n limit, meaning that you have to still contract this disorder line. So so you can now look at this diagrams, and essentially you see that how many summation indices are here over here. So you see that I have essentially a summation. So remember, this Jij comes with a factor of 1 over 2n to the 3 by 2. Okay, so that's because you want to get an extensive energy. So this diagram, for example, will have a factor of n cube, because you have 4 vertices. Okay, and then sorry, this will be n6 because you have 4 vertices. And then you have this summation. So you can see how many summations I have. I have basically 1, 2, 3, 4, 5, and 6. Okay, so that so basically these 6 summations, all these things will again give you a factor of n to the power 6 here, and that will give you a order 1 contributions for this diagram. Okay, however, this diagram you can see that I have essentially one less summation in this. Okay, because I have to contract like that, and that so when you do this, it is 1 over n to the power 6, and here you will get 1 over n to the power 5 when you do these 5 summations, and that will give you a separations of order 1 over n. Okay. So this is how, I mean, just from the diagrammatics you can see the large theory why. So this is the only diagrams, at least up to the this fourth order that I did will stay, right? But now of course you can do all these things here, right? And then you can make this full thing as a full Green's function. Basically you don't need this, you make this the full Green's function, and that was the diagram that was drawn. Okay, so so this is the sort of the diagrammatic way to do this. I'll discuss the G sigma action now, because that also gives us some other ways to analyze this, especially fluctuations around this large N much easily. Okay. Okay, so let's do this G sigma action. So first, so we are going to calculate, just write down the partition function, Euclidean partition functions for this model. And of course, when you write down these Euclidean partition functions, it will depend on the disorder realization, right? Because I have now this disorder here. So, so in principle, so this is a complicated object which depends on all these couplings, okay? Ji, J, K, L. All the set of couplings on the n number of sites that you have. So you will get a quantity which depends on these couplings or these disorder couplings. So now, so this action, so this of course has some bare part, and then okay, so that's the thing, and then this S naught is this corresponds to this Green's function. Okay, so this is the action that you get. So now what you want to do is you want to of course don't look into this all these greens. So you want to of course solve this interacting theory, but you don't want to do it for each disorder realization, because that's impossible, okay, to do. So to do that, so now you have to do the disorder averaging of this theory. So the question is that how should you average this? Should you average the partition function, or should you average some other quantity? So it is of course a well-known thing in disorder systems, which has been studied for very long, many years, and particularly mainly to start with spin glasses, and the idea where people have used or dealt with this kind of theories a lot. And the main thing is that you can't really average the partition function, because this quantity is not what is called not self-averaging quantity. Okay, so you can't really average this as so. What is a better thing to average? I mean, which you can show it's self-averaging, which is the free energy. Okay. And there is an argument for this which is known as Brought's argument, which I am not going to give it now, but it's a very simple argument which you can give, which justifies that if you have extensive quantities like free energy, then you can show that for an infinite system it's a self-averaging quantity. Okay, so these are slightly trickier if you have time-dependent correlations functions, but you can still show that sort of local correlations functions are generally self-averaging. Some cases it can be violated for example, if you have things like conductivity and conductances, then the self-averaging properties can be violated, as well known for in the situations of Anderson localization. But generally, for free energy and thermodynamic quantities, this you can show that it's self-averaging for a large system. Okay, so you have to average this log z, but then averaging log z over this disorder is difficult because you can't directly average log z because z is given by that expression, which is some functional integral. Okay. So the trick that is used is a well-known trick in the disorder system, which is called the replica trick. Okay, it's similar to the replica trick that is used for the entanglement entropy, although the replica limit is different here. So here what you do is you can always easily write this log z as so you can always write the log z as this. Okay, so this is just easy to show, just 2 lines, and then you can average this, and then the average will only go to this. Now, so this is the replica number n, which at the end of the calculation you are supposed to take n going to 0. So So now this, of course, when you do this, particularly for this theory that we will do, also that you at the end you take n going to 0 limit, but so there is a interchanging of limit that will happen here because we will first take sort of. So the question is that how should you take this n going to 0 limit? Should you take the thermodynamic limit first and then going to take n going to 0, or the other way around? So for the calculations, typically you will just take, so in this case actually it doesn't matter, but generally you take the thermodynamic limit for the calculations and then try to take n going to 0 limit, okay, which may not be valid. And secondly also this, just like any such calculations, so you don't really know the analytical properties of this analytical continuation. So this has caused a lot of problems in spin glasses, that whether you can actually analytically continue this result. But for the SYK models and all, this turns out to be, at least from the numerical calculations and also some other works, it's known that this limit works, especially because you can also get the same results by the perturbation theory.
So,
Yeah. Right. So but if you can have also, so the question is, if you have other type of large saddle points like replica symmetry broken ones, so there it become tricky, right? Because how do you really, so once you break the replica symmetry, then you have to take an ansatz for how the replica symmetry is broken, and there of course this issue of how you take the limit can be more tricky, which is the case in spin glasses. Yeah, so there are several works on this. In fact, I think Raghu Mahajan also has worked on this, and other people, so analytically and numerically. So of course the standard thing is you do for finite n exact diagonalizations and try to compare, try to see whether you have some kind of indication of replica symmetry breaking. So that has not been found. Okay, and also from analytical calculations you can show that this replica symmetry breaking effects come at much smaller energy scale, which is exponentially small in this n. Okay, basically it comes in a temperature scale which is less than e to the power minus n, so which doesn't really come under these large n theories. Okay. Okay. Okay, so once you do this, then rest of the thing is simple. So, so the basic step is here. So I'll just sketch the basic step of this derivation, or without going through the whole thing. So the main thing is, now once you assume this, so then you just replicate this partition function. So effectively you just take this partition function and then multiply essentially n number of this partition function. So when you multiply this, is just each one of them is integration. So you will have n integration variables, right? So this will have one index here, okay, and this index will go from 1 to n. Right? You just replicate this partition functions n times. Of course, at this stage, these replicas are not coupled. They are still correlated because they feel the same disorder. So this correlation, you will see that when you average over this, because they have the same disorder, but through disorder they will get correlated. Okay. Okay, so let's just try to do few steps of this averaging just to see how it goes. Okay, so when you are doing, so now what I'm going to do is I'm going to do this averaging over the disorder uh, with this Gaussian disorder weight, right? So you have to remember that when you are doing this, then all this, so all these JIJKL are not independent because there is an anti-symmetry property and also there is a hermiticity property. So you have to take those into account correctly, but that's just combinatorics. So that's why this thing comes here. Okay, so you'll just, so because you are just doing a complex Gaussian integration, you just the standard complex Gaussian identity that you use. So you just integrate out this JIJKL, and at the end what you will find something like this. I'll just writing the final result here. Okay, so this is what you will get if you do this. So now here where the large n essentially comes, so you see that because of this, so now you have these kinds of objects that are coming here, which you can define as some okay, so you can define some new fields now, which are just combinations of these fields. Now the thing is that of course these objects are completely fluctuating. So if you look at a given site here, so these are of some fluctuating Grassmann number. Okay. Now the main thing about large n that comes here is that when you, because of this large n model and all to all connectivity, ultimately what you can do, you can define a new variable which depends on sum of all these fluctuating fields. Okay. So yeah, that's right. Yeah, so this is V. Yeah. Right, so you have basically some of this many sort of fluctuating fields, so that's why you expect that these things will have a large n limit, okay, because essentially it's like going like square root of n, right? I mean, of course, these are Grassmann number, doesn't have a value, but roughly speaking, in some expectation sense, this will become small, okay. So this will be a well-defined large n field, and then what you do is you write now. Yeah, so now you introduce this thing in the field theory. Once you identify these new variables, so you introduce just an integral over this these fields, and to impose this condition that that I'm doing this, bringing this new variable, you just put a delta function here. Okay, so you just impose, and then I have the rest of the thing. some S effective that emerged because of that calculation. Right, so you impose this, so this I am just imposing, this is of course exact, right, because I am just saying that I define a new variable, so this is one way of defining the new variable. And then what you do, you write this delta function using just a standard method, so essentially this delta function you write using some. Okay, so I just exponentiate this delta function, bring another set of fields. Okay, so I just write the delta function as an exponential here. Here I am not putting any I or anything, that doesn't matter because at the saddle point level that will be chosen. Okay, so I am just writing some kind of complex Fourier transform. Okay, is that okay for the people who have not in this? So now effectively I have a theory which has this fermionic thing and this G and sigma fields, okay, which are bilocal fields. And so if you see, so by doing this, so essentially what will happen is that since you introduce this G equal to that C bar C, and you introduce this, so now you will see that because of this definition of this large n field in fermions, this is now a completely Gaussian action. Okay, so basically if you just write the fermionic part that is left after doing this, so then you get some kind of S effective here, which is C bar C G sigma. Okay, and then the fermionic part of this effective action. Okay, so that just looks like. Okay, so this is what you get. So there is of course the other part. Let me write just one term of that other part. So the other part. Okay, so this is what we will get for the action after doing this. So now since this is completely Gaussian, so you can just integrate out this object. Okay, yes. What is the information of? Yes, so that is there in this A. So this A and B, they go from 1 to n. Okay, so this some number of terms here, that small n comes. Okay, so you can identify. So basically, this object. So this defines some object like delta tau sigma here. That I'm just writing it shorthand notation. So some delta tau operator and sigma, which is bilocal operator. And so if you just integrate out the fermion, then you'll just get a trace log of that object. Okay. So this part of the action, if you just integrate out the fermions, you'll just get this trace log thing. Okay, so that finally gives you the sort of the G sigma action. Yeah, so that's whatever I load there. So this delta tau sigma and then rest of the term, yeah, same. Yes. Yes, so this is quartic in G, right? This is of course still interacting. I mean, you cannot get rid of the interaction in the theory, right, by doing this transformation. Okay, so now, okay, so another thing is that this, when I integrated this fermion, so, yeah, so, okay, so right now I'll, so one thing, what you do here, so one additional thing that you have to do, which is that now I have these replicas here in this action, so this AB. So to solve this problem, you have to assume some structure for the replicas, okay? And so the structure, so it's essentially it's like a order parameter, this G and sigma, right? So this is a matrix in tau and tau prime and AB. So if you are trying to solve a mean field theory, you have to take an answer, right? If a ferromagnet, then you take a ferromagnetic order parameter like that. So you have to assume if it's an anti-ferromagnet, then you take this staggered pattern. So write that in the replica space, you have to also take an answer. So how does it look? So how does this matrix look in the replica space? And of course, eventually you have to take n going to 0 limit. So it turns out that in this case, in the case of SYK model, as we discussed, so it is enough to take a structure where this object is just G tau tau prime. So this is a replica symmetric and diagonal ansatz. Okay, so you take this ansatz and you put it there. So if you take this ansatz, then of course you don't have any off diagonal terms, so everything become A. And because it's replica symmetric, so it should not depend on A. So you don't need any index here. Okay, so none of these are needed basically. And so then when you do this fermionic part, it's just basically n copies of this fermion. So the small n comes out here, right? And similarly for this, from this summation, because this summation first of all become diagonal and then there are n terms. So there is a small n comes here. So, so effectively that's the action that you get. Yes, please. Yeah, just, yeah, go ahead. No, only sigma is there. Yeah. No, it's a quartic. Yeah. Yeah. So this what you are saying will work for the earlier random matrix model that I did. No, no, no. So you don't want to use any further large n approximation. So you have already used everything. So now you want to treat it exactly in this limit. Okay. So meaning that. Already assume. So to show that it is the effect is at much smaller scale, you can assume that some structure of the replica symmetry breaking. Okay, and put it there, and then you can do some calculation and show. Yeah. Okay, so now as you can see that I can easily now take this n going to 0 limit, right? Because small n going to 0 limit, because I can just okay, so two things. So first of all, I am going to so there is a large n, so I can just take a saddle point n going to infinity. So I just only need to consider this this saddle point. Okay, and in saddle point, so this action, so this partition function will be evaluated for only that saddle point action, and then I can take n going to 0 limit. So I'm taking large n limit first and then small n going to 0 limit. So I just expand this, then essentially I just expand this exponential e to the power n capital N saddle point, right, minus 1 by n, and then I'll just get that the free energy is just given by the saddle point action. Okay. So basically this is how here this replica limit is very simple. So that will give the saddle point equations that I wrote earlier. Okay. Okay, so maybe I will go back to the slides. So this is this is the derivation. I mean, it's quite straightforward, as you can see. Derivation of the saddle point. Can I have the slides back? Yes, please.
Since there is a summation running from 1 to n, I'm a bit worried if there is anything bad happens around n equals to 1. But
you are meaning small n or capital?
Small n, sorry, small n.
No, so here you have to take n going to 0 limit, right? So once you assume this, so you are asking, you are worried about the n going to 0 limit or n?
This calculation is based on n larger than or equal to 1, right?
It's based on n being integer, right? So of course I am going to take n going to 0. So let's say I have this for all integers. Then I want to analytically continue to n going to 0, which is of course ill-defined, right? Because I only have the results for integer n.
Yeah,
so in general, something bad in principle can happen. Okay?
So what kind of consistency, is there any consistency?
Yeah, the consistency check till now, as somebody asked earlier, is only through sort of numerics and trying to take different kinds of replica answers and trying to see whether they contribute, whether there could be some other replica answers which is better than this. So they, of course, I mean, you have to assume some answers, right? So that's the only consistency. Okay, so that's the origin of this. Yes. You mean the free energy? Yeah. So the free energy. So if I calculate the saddle point, then the free energy will be just the saddle point action. So evaluated with the saddle point Green's function and the sigma, and that is given by this saddle point equation. Okay, so in addition, of course, because I am dealing with a complex SYK, I have to also tune the chemical potential to fix the number of, because I am working in a grand canonical ensemble, so I have to fix the chemical potential. Okay, so this I discussed last time. Okay, I wanted to work this on Blackboard, but okay, I'll probably skip because I want to discuss some few more things. So this is actually very easy to see, I mean, which is already I have written here. So you can, I mentioned this last time. So just like earlier, as I told that if you are trying to look at whether it's a Fermi liquid or non-Fermi liquid, you try to compare the self energies sigma omega with omega for omega going to 0. So that is equivalent to comparing it with this term, which is this delta tau term. So if you take an answer as that there is a non-Fermi liquid, so you just neglect this to start with. Okay. So if you neglect this, then you can rewrite this Schwinger-Dyson equation in this form, and then you see that once you have this, of course it has to be ultimately self-consistent, but if you have this somehow, then you see that there is a very large symmetry of diffeomorphic symmetry that comes here, because you can now reparameterize this time variable in this equation by some arbitrary monotonic function, differentiable function, and then you can redefine, you can define a new Green's function which is defined by these relations. Okay, so basically I had this, I am doing a transformation here. So this tau and tau 1 I am replacing with f sigma and s sigma prime. So I try to rewrite this equation along with this equation. Okay, so the self energy equation. So then I will see that there is this large symmetry that appears, that if you redefine your the g and sigma like this, then this equation doesn't change. Yes, so this, huh? Yes, it's exactly coming from that, right? Yes, that's right. Okay, so for this particular case, because of I'm dealing with a complex fermion, so for Majorana case, which I mentioned, that you can actually show that this g tau tau prime is just minus g tau tau prime tau, but here that is not true. So this tau and tau prime are separate. So as a result, you have some additional in freedom. You can add some factors like this. Also, it will not change the saddle point. So these are some emergent U1 factor. So in this complex SYK model, you have two emergent symmetries at low energies. One is this emergent U1 symmetry and another this reparametrization. Okay, so both emerges in this model.
Sumilan, you can take it to be a phase because why does it have to be a phase?
So it is here, of course, it's in Euclidean time, so it's a real number. It's not a phase. But if you continue, so here at this stage, it's not a phase. Okay, so you have to actually fix it using some KMS boundary condition. But it's at this stage, it's just a real number that can be there in principle. Okay, it's not a phase here. Yeah.
Some boundary conditions fixed.
Yeah, fix it. Yeah.
Sorry,
Yeah.
can I just go back to this
Right.
free energy calculation? Did you say, how do you check that replica symmetry breaking saddles don't contribute to this?
No, so there is no, so people, as I said, so some people have already tried to do away from this replica symmetry breaking, replica symmetric solution. So they took, but you have to take some ansatz. So there are some well-known ansatz for this which come from Parrikar, which has been used for spin glasses. So you can try at least those ansatz, which are this one-step replica symmetry breaking or infinite step replica symmetry breaking. So some people have tried those ansatz. So you can put that. Another thing you can do, which is a standard thing, that you can put some small. So you have this GAB. So you are assuming that this is G, right? So basically this form, and then you can put some fluctuations to this, right? And you can try to analyze the stability of this solution, stability of this functional by expanding in that. Right, and so there will be some fluctuation matrix. So you can try to see at least it is stable or not under replica symmetry breaking. So it is found to be stable till, as I said, this small temperature or small omega, which is like goes like this. Okay, so at very low energies, of course, it requires finite n. So large n, this is always stable. This replica symmetric solution. But if you have finite n, then you can have replica symmetry breaking. But that happens at very small energies. Okay, so once you have this kind of reparametrization symmetry, so you can try to guess some power law solution for these Green's functions. So I actually wanted to work it out, but maybe I'll skip it for the time being. So you can find this in many references, including here and some other references. This symmetry. So it's it's right now it's just a symmetry of the saddle point. What does it do? I'll discuss a little bit. Okay. So only thing I am saying is that this, if you neglect this term, then you can write down the saddle point, and it has this symmetry under this transformation. Okay. So right now it's just that statement. I'm not making any further statement. So you started with the model in the UV. It didn't have any of these symmetries. Right, but if you are looking into low energies, then this symmetry is this reparametrization and this U1 symmetry that emerges. So it's the emergent symmetry of the low energy theory. Okay, so how this theory affects ultimately how this symmetry affects the low energy solutions, that we'll try to see. Okay, so right now it's just a statement that these equations are this equation is invariant under this transformation. This equation plus that equation of sigma equal to it's just a statement that this equation along with that this equation is invariant, okay, under this transformation. Okay, so what you can show that so now once you assume that, so what you do is you assume some kind of a power law solution, and then you try to put in this equation. Okay, so the way I'll just so the way you try to see this, I mean it's actually just some algebraic manipulation. I mean, yeah. So what you do is you assume that let's say I assume this particular form of the solution. So where this lambda and this theta, everything I have to fix by the self consistency. Now this theta has some constraint. So this theta has some constraint because imaginary part of g r omega, that has to be less than 0. Okay. So if you try to impose that constraint, taking into account both positive and negative omega, then you will find that this theta must lie between minus pi by 4 and pi by 4. Okay. And theta equal to 0 is the particle hole symmetric case, because you can see that if you theta equal to 0, then the spectral, so you can calculate a spectral, sorry, yeah. So if you can calculate a spectral function from this, and in the spectral function, depending, so if you have theta 0, then you will see that the spectral function, okay, whereas if you have some non-zero theta, then the spectral function will be asymmetric. Okay, so this theta essentially controls the asymmetry of the spectral function, and thus it is related to the number of fermions, as I will discuss a Lattinger theorem for this determining this theta. So it is actually related to the number of fermions, and so as you know that if I have a half field system, so I have a band and I have half field, then it will have a particle hole symmetry. But if I am go away from half filling, because of the filling, you are breaking the particle hole symmetry, and that's where this spectral function will become asymmetric. Okay, so that is controlled by this theta. So what you do is you take this this solution, this answers for the Green's function, and then use from this you can try to calculate g tau. Okay, so there are standard expressions. So for example, this g tau for tau greater than 0 will be given by okay, and then there is some expression for tau less than 0. So if you know the spectral function, you can calculate g. One such, you calculate this g tau, sigma tau, and then eventually sigma omega, but they have to match here. Okay, if you try to match them, then you will give you the results for the lambda. Okay, and you can see that this is a self-consistent solution. Okay, because they will match. Thank you. Theta is not fixed by this argument. Okay, so but theta has to be within that range because of the.
Finally, theta should be fixed by mu, right?
Yes, yeah. Okay, so now, so I'll try to discuss this. So now, what happens is that it turns out that so this is one. So the one thing. Okay, so I should mention. So this is a self-consistent solution. So from this self-consistent solution, you find that the self energy actually goes like square root of omega. So this is your non-Fermi liquid, because square root of omega is always larger than omega for omega going to 0. So that's what we started with, right? Defining the non-Fermi liquid. So this is essentially giving you a divergent spectral function, okay, because this has this typical SYK like divergence, and so this is the result of the single particle spectral function. So now it turns out that you can, I'll try to sketch this calculation a little bit. So it turns out that using this saddle point solution, you can actually try to calculate the entropy of this SYK model, and if you take this limit, so in this calculation, in this large n calculation, I am first trying to take n going to infinity limit, and then I have a result for some finite temperature, and then I take t going to 0 limit. It turns out that if you take the limit like this, then this SYK model actually has a non-zero entropy at t equal to 0. Okay, and this is essentially coming because so this I'll show some exact diagonalization result. This is essentially coming because close to the ground state, SYK model has a very dense spectrum, which means the many body level spacing is actually exponentially small even close to the ground state. So typically, if you take any bounded system, any bounded many body system, if you go to large high energies like middle of the spectrum, so then you will always have level spacing which is exponentially small. But standard conventional quantum many body model, if you go to close to ground state, then these level spacings are typically just order 1 if you have a gap system, or order 1 over n, or 1 over n to the power some power for gapless system. So the many body spectrum will look like that. So SYK on the other hand has a many body spectrum near the ground state which looks like a high energy spectrum, okay, a spectrum at high energies. And as a result, when you are taking n going to infinity limit, this level spacing is going to 0, and as a result, so now you have a finite temperature. So essentially within that temperature window you have exponentially large number of levels, and that is giving you this entropy, okay, as you are going to take t going to 0 limit finally. So that's the origin of this, and you can so now you can sort of see this demarcation between for example, this non-interacting model that I showed earlier, this is the many body spectrum which is much sparse near the ground state, whereas you can see that this is for some finite n SYK model, I think 32 sites or something, 32 sites, and then you find that this has very dense spectrum at low energies. Okay.
Is this computation actually consistent in the sense that we're taking a set point approximation, we're obviously forgetting about fluctuations, because
Yeah.
they're small, but they're big at large at small temperature. So are they consistently neglected, or are they just?
Yeah, they are. So sorry, can you repeat?
There are large fluctuations at small temperature.
Yes. Right.
To saddle point, you are basically neglecting
Right.
at least
Right.
one notion of fluctuation.
Right.
So
Right.
the
Right.
question
Right.
is this prediction that t going to 0
Yeah.
in fact is that a well-defined approximation?
Yeah. So what happens is if you yeah. So this I don't have the data. Maybe I have it later. So.
That curve also.
Yeah, so this is of course a large n curve, but so answer to your question, so people have done this finite n calculation. So what you find that finite n calculation, this entropy will continue at some temperature, it will go to 0, okay, and this temperature, so if it is correct, then this temperature will become smaller and smaller as you go to n going to infinity. So that you can check. So that way it is consistent. That means you can approach this limit if you are trying to take this t going to limit 0 going t going to 0 limit like this. That is, you do the calculation for finite n and then see how far this goes. This continues with the curve, and then if you increase n, then this goes down and goes down. So that way it is consistent. Yeah, yeah, right, right, yeah. Yeah, yeah. Yes. Yes, yes. So this pi. So first of all, you see that pi by 4 is the limit. Okay. So basically, I'll show this. So this pi by 4 limit corresponds to completely filled band. So it's like there is no, you can't do anything, no dynamics. Yeah. Okay, so now let me discuss this. So you can actually analytically calculate this zero temperature entropy. So the result I showed is from large N numerics. So the kind of saddle point solutions that I mentioned last time. So from that, but you can actually calculate it using a kind of what is known as Latinger theorem for the non-Fermi liquid. So the question is that what controls the theta, and as we discussed that theta would be controlled by this ultraviolet physics, which is the N, okay, the density or chemical potential, which is of course the density of the full band. So it's the ultraviolet thing. I mean, you can't just look at omega near omega going to 0 and decide this, but it turns out that there is a way to do that. Okay, even just using this low energy solution, you can actually find a relation. Okay. So this is a result of this beautiful Latinger theorem, which you can be applied here. So in the standard Latinger theorem is applied typically for sort of interacting fermions when they are in this Fermi liquid state, and what it does, it connects the volume of the Fermi surface in the interacting system to the number density, and in particular it says that essentially there will be always a region which you can demarcate as full or empty depending on where the Green's function, the interacting Green's function at omega equal to 0 changes sign in the K space. Okay, so that essentially connects the number density with Kf. Okay, so this is of course obvious for a non-interacting system, but not so obvious for interacting system. So this is what Latinger theorem does. If you assume certain properties of the Green's function, mainly its imaginary part goes to 0 at omega equal to 0. Okay, so that's like a Fermi liquid. It's true for Fermi liquid. So it turns out here there is a Latinger theorem even for a non-Fermi liquid. So let me just sketch the derivation. So for this derivation, what you need is so what we discussed is the conformal solutions. I'm just going to call it conformal solution, which is this 1 over square root of omega solution. So this gives you the limit when omega going to 0. Okay. Now, of course, it turns out that you also know what happens to the omega going to infinity limit, because there are some constant because of the anti-commutations and all. Okay, so you know how the Green's function should behave and self energy should behave as omega going to infinity. So it turns out just these two information is enough to connect the theta with the n. Okay, and so I'll skip the full detail. You can find it anywhere. So just the basic idea is that you can write the density, of course, with the full Green's function. So this is the time order Green's function, not the retarded one. And then, of course, this has some relation with the retarded and advanced, and they are related. Now you can write this. So basically, you can write this thing using the Swinger-Dyson equation. You can rewrite this equation on the right hand side like this. Essentially, some logarithmic derivative of logarithm of g, and then some term which is self energy. So in the Latinger original derivation, one could show that this term actually goes to 0. Okay, that you can show using some skeleton diagrams and its transformation properties. So here it turns out that this is actually not 0, because so this goes to 0 typically if you have sort of well-defined Green's functions at omega going to 0, but here the Green's functions actually diverges at omega going to 0, and as a result this term turned out to be not 0, or this term is not 0. So you have to actually evaluate this, unlike in the Latinger case, but you can evaluate it in this particular case using some regularization. So in any case, the first term is much simpler. So first term you can rewrite like this, and then effectively you have this derivative of log, which ultimately if you try to do the integral, it will just give you the arguments of this retarded Green's function, right? Because Green's function is a complex quantity, you are taking log and taking derivatives, only the arguments will stay. And those arguments of the Green's functions are determined at omega equal to 0 by conformal solution, at omega going to infinity by this constant because of the anti-commutation. And from that you can actually find out these integrals, okay, using this. So this is the result of the first one, and this is the result for the second one. And as I said that this term, which is slightly trickier, you have to use some principal value regularization. And you can calculate this, which was done long ago by Parrikar, Georges and Sachdev, and which can be found here. Okay, so at the end you find this nice result that n is just given by this simple formula. Okay, so n is just related to theta like that. So this theta, if you wish, is like a kf for the non-Fermi liquid. So now how do you get entropy from this? So for getting entropy, you have to use some kind of a Maxwell relations between the entropy and the chemical potential. So in this model, you can also show that at low energies, the chemical potential is also given by this theta. Okay. So this eta is just a regularization, is 0 plus. Okay. It's just a 0 plus, yeah.
Little n is what? The total fermion number?
Yes, yeah, total fermion number per site. Yeah.
No, site here means what?
Oh, the SYK side, like, so basically you have n, small n into, this n is of course not the replica n, yeah, so basically you have total number which is small n into capital N.
Okay.
Yeah,
So,
yeah.
divided by
Yeah. No, so it does contribute. So basically, because you have a log, it will be essentially the argument of gr at infinity and 0, and one you will find is forgotten, pi by 4, another is 0 or something. Okay, so there is a relation between mu t and theta that you can find. I mean, this is not exact relation like the Luttinger one, but it's sort of expansion in low temperature. But this is enough for this derivation of the low temperature entropy. So then once you know these relations between mu and theta, then you can actually connect. So you can write the entropy as using this object del mu del t, which is given by this. So it's just the integral starting with some reference state. Okay. So now this reference state you can take as completely empty or completely full state, which will not have any entropy because there is nothing to do there. So and those are the limits pi by 4, plus minus pi by 4. Okay. So that's where the conformal Green's function goes to 0 also. The self energy goes to 0. So this is 0. So then this is the result, and we have already found theta n as a function of n, right? So that was the Luttinger theorem. So you can use that result and you can just integrate and you will find that the S0 is given by 0.46, which is if you extrapolate, it's very close to this value. Okay. So this result is quite interesting because, as I said, the only knowing the low energy thing you can find this. Okay, this ultraviolet result. Okay. So now let me discuss a little bit more of this. So this, as I said, that this yes. We didn't, yeah, but we only needed at omega going to infinity. You could have thought that you might have needed even at some intermediate omega, right? Yeah. Okay, so as I said that the saddle point in the conformal limit has this large symmetry. So of course the saddle point that we found, which is this Pawel law, of course breaks this symmetry, right? Of course the saddle point are not invariant under reparameterization. So this is the example of standard mean field theory. Like if you take the standard Ising model saddle point, which is m equal to tan hyperbolic beta z m, so then of course that has the symmetry going m to minus m. But when you find a solution that breaks the symmetry, right, which is either m plus 1 or m minus 1 at 0 temperature. So it's like that. So here the saddle point also breaks the symmetry, but it still has a symmetry of SL2R, which you can easily see that just by putting. So you have some this special you can do this linear transformation, fractional linear transformation. And you basically see that you put it in the this equation, which is the transformation of the Green's function, then it remains invariant. Okay, then so this SL2R symmetry is still there. So essentially, you have a manifold of low energy modes, which are this d phase 1 modulo this SL2R. Okay, so that manifold is there. So now, of course, it's obvious what that manifold would be, because or what are the low energy mode would be, because so you now what you want to do is you try to write down some fluctuations around this saddle point, and what you try to do is you, of course, when you writing as a standard thing that so you want to, let's say, so you have this action and I have found the saddle point. So now the idea would be that you expand this this action around the saddle point. Okay, so with some delta G. Okay, so the idea that one uses is that so you try to generate this delta G using this reparameterization. Okay, so basically you take the saddle point solution, so which I am calling the conformal solution, and then you generate a new G. Okay, so just like we were doing earlier, so I generate a new G by doing this. Doing this transformation. Okay, so I have the saddle point. So now I do some arbitrary reparameterization. It will change my Green's function. Okay, and then I can try to calculate the delta G, which is this G minus the GC tau tau prime. Okay, and then I can try to evaluate the action. So of course this action is already constant because you know that the saddle point doesn't change under SL2R. So whatever action you write should be invariant under SL2R. Okay. So and that is so it has to see, I have just written it in detail, but essentially it has to be invariant under this kind of transformation. So that already constrains the action to be Schwarzian. Okay, so that's the action that you can write with the lowest. No, it will. I didn't write. You do that also. You change both. Okay, yeah. So this obviously just fixes the action, and here because there is a U1, there is also a U1 term that will appear, which also will be very standard looking U1 term, which is just delta tau theta square. Okay. So there is apparently here it looks like there is a coupling between the phi and the U1 field and the reparameterization field, but this you can sort of gauge away by doing a transformation, okay, on the phi. So it's basically they become decoupled. The U1 field has its own action and the reparameterization has its own action. Okay, so they don't really couple. And then you can try to do a lot of things. I actually myself have not really worked on this much, but a lot of people have done. So one question first you of course ask, from symmetry this is fixed, but how do you know these coefficients? Okay. So the best way to fix it is just do the numerical saddle point calculations and you try to fix this from this, but then you can say, okay, if I can solve it, what do I gain from that? So the gain is that now once you have this action with this coefficient fixed, you can actually calculate finite n corrections, okay, using this action, okay, so which you cannot do by the large n solution of the saddle point. So that you can do. You can also think about doing quenches and even entanglement calculations and things like that with this Schwarzian action, and it will give you finite n corrections. So one example of this finite n corrections are people have already obtained. So if you do on the large n going to infinity, then because of this action you get these additional terms. Okay, so you get these additional terms which are basically look like a specific heat type terms in the entropy, and then they are fixed. They are given by these coefficients which appears here in this action. So from this you can fix this k and gamma, these two parameters, and then you can go on further and then try to obtain. So there are some other ways of fixing this. I mean, different people have use different kinds of ways to fix this analytically, and there are some interesting works along that line. But let me just come to the sort of the main result of this. Is that you can calculate some finite n corrections, okay, which is like, so these are order n and this is order 1. And you can also see from here that when this order 1 term become comparable to this, which is like exponentially small scale, okay, where the finite n corrections will become important. So that is in that way it is consistent, and using this you can calculate the basically many body density of states, and you can find out some analytical results for this at low energies. Okay, so that's what you can get if you do this Schwarzian calculation. Okay, so there are some other things also happens at finite n, how it changes the results. So I told you that at infinite n, the spectral function of the Green's functions goes like 1 over square root of omega. So it turns out if you take the Schwarzian corrections, then this result changes at omega going to 0. It actually goes like square root of omega rather than 1 over square root of omega. Okay, and there is a crossover scale which is essentially like 1 over n. 1 over n log n actually, but yeah, which is here. Okay, so you can also calculate finite n corrections of this theory.
But this crossover again probably is some 1 over certain energy suppressed in n.
Yes, it's just a 1 over n correction. Yeah. So you actually don't know how to include this effect completely, right? This exponential. Yes.
The fluctuations I was concerned about earlier, they showed up there. So you have in the free energy a T log T, and that goes to 0 nicely.
Yes, right.
But in the entropy, you have a log T.
Right. Yeah.
And that does not work so nicely.
Yeah. So ultimate.
The numerical plots actually seem to work.
No, it will always go to 0 eventually, right? So even if you always take the limit that you have finite n and do finite temperature calculation, so it will you can never get this 0 like finite entropy at 0 if you try to take the limit. So that way, yeah, it will not work. That's true.
But when
Yeah.
you had that full density of states, that had the sign hyperbolic,
Yes,
right?
right.
That goes to 0.
That yeah, that's right. Yeah.
So there, at E equals E naught, the ground state. With the full one loop.
Yeah, that's right. Yeah, but still, I mean, the thing is that if you take the limit other way, you will always get a pure state, right? You will not never be able to get it. So if you take always the limit that you do the calculation for finite n, right, and then try to take the, and then t going to 0 limit, and then take n going to infinity, that will always give you the 0 entry. Yes. Okay. So I have 7-8 minutes. So let me just mention. Okay, so let me just mention a few more things, kind of bit quickly. So I'll in the next lecture I'll discuss some calculation of entanglement in this model. But today let me just little bit end with some discussion of some interesting thing that you can do with this model. Okay. So one question now would be that, okay, so this is a non-Fermi liquid fixed point, but can you change the fixed point, right? Can you do something on the model so that you get some other fixed point? So for example, Fermi liquid. So it turns out that is very easy. So if you just add a quadratic term, so this quadratic perturbation is always relevant. So you can see from the scaling dimensions that I wrote. And you can also see directly from the large n saddle point. So if you do this calculation, so I already discussed both of these separately, right? So you can now have two self energies, one coming from this random matrix which I discussed in the last lecture, and one from this. And now you have to solve these equations along with this. So you can see that now no longer this 1 over square root of omega is a self-consistent solution. Okay, so you can just take this ansatz and you can put in this equation. You will see that this term t square over 1 over square root of omega will dominate in omega going to 0, and that will tell that your g omega is square root of omega instead of what you started with, which is 1 over square. So it's not self-consistent. Okay. However, you can see that the free fermion ansatz, which is the result for the random matrix, still self-consistent, and in fact you will find that it is like this result. So it's basically like a Fermi liquid. Okay, if you add this quadratic term, and you can actually show that it's a Fermi liquid, it has some omega square self energy and things like that. So there could be some interesting effect at finite n, which is some kind of many body localized or non-ergodic states also can appear, but let me skip that. So let me just mention, so this of course will immediately change the fixed point to a Fermi liquid, but can you do something better? So can you sort of tune it from a non-Fermi liquid to Fermi liquid transition? Okay, so this somehow it turns out that if you do a simple modifications of the model, you can easily achieve this. So the modification of this model is that you take the SYK model, and if you of course add the hopping term, the quadratic term in the SYK fermions, then it completely changes the fixed point. Okay, it makes the non-Fermi liquid a Fermi liquid. So you want to still preserve the non-Fermi liquid, at least for some extent. So it turns out that what you can do, you can add some extra set of fermions, some other set of fermions, which are defined by random matrices, and then they are coupled quadratically with these fermions. Okay, so this is the model, and this model also can be well defined in the large N. So in this limit that, so there are basically m sides of this psi fermion and n sides of the C fermion, and you take the large N limit such that this m by n ratio remain fixed, which is P, as n and m goes to infinity. So it turns out that this model has a very interesting phase diagram. So what you find in this model is that it has a exactly solvable non-Fermi liquid to Fermi liquid transition. So as a function of this P, you can go from a non-Fermi liquid state to a Fermi liquid state. So this non-Fermi liquid state is exactly what I showed, is the SYK non-Fermi liquid. It has, if you look at the C fermion, then it has this 1 over square root of omega divergence. And here additionally you have this psi fermion which has a different behavior, okay, but it still remains a non-Fermi liquid. You can exactly show that this has a Lyapunov exponent which is exactly 2 pi t, okay, and up all the way up to p equal to 1, and this transition doesn't depend on any coupling constants of the model, okay, it just depends on this ratio p equal p. So it doesn't depend on t, j or anything of this model. M over n, yeah. And then you go to a Fermi liquid state where you can show that it is t square, and you can show that there is a transition in the level spacing. So that the level spacing across this transition goes from having this behavior to this 1 over n. In fact, you can, using a Luttinger theorem for this model, you can exactly calculate analytically this entropy, zero temperature entropy, and it vanishes at p equal to 1. Okay, so these are sort of exact results in the large N limit. So in some sense, if you have some black hole interpretations, then essentially this entropy is going away and is going into a transition. Okay, these exact transitions here. So another reason that this model is interesting, because so I wanted to discuss little bit some realization of the SYK. Maybe I have like yeah, I have 2 minutes and 5 more minutes, right? Okay, so let me then discuss this. So yeah, so I'll probably, so let me just for the end of this, I'll skip this because this model I already told you. I mean, the calculations are very similar what I mentioned, so I'll just skip this point. I wanted to discuss some experimental realization of this. Okay. Okay, so now, sort of slightly change of gear, but I'll try to connect with what I discussed. So now one question is that, can you realize SYK model in condensed matter system? Okay. So it, and of course people started thinking about it, and there are several proposals. So, so what you are trying to realize is this model. So either this Majorana model or this complex SYK model, okay, whichever is easier to realize. Now, what are the challenges of realizing this model in standard condensed matter system? Of course, you can see that this cannot be a standard condensed matter system because it's like all-to-all connected model. There is no sense of space in this model, right? And so if you look at the challenges, I mean, if you are trying to realize that the Majorana version, then there are very big challenge, because you have to first realize Majorana fermions in condensed matter system, and there are a lot of controversies and debate. I mean, we thought that we have realized it, but situation seems to be much more questionable in recent years. So we don't really know whether we have realized it that much. And of course, even after you realize it, you have to still construct this model using those Majorana fermions, right? So that's a problem. So the solution could be try to use the complex fermion, but even there, generally you will always have some quadratic term, right? So quadratic term will be always there. I mean, you can have the quartic term, but quadratic term will invariably come. So then the idea is that you try to use some symmetry in which you can manipulate in condensed matter system, so that these terms are not allowed, okay, just by the symmetry. And then the third thing is that you have to have this non-locality. So the standard model of this kind of thing in condensed matters are what are called quantum dots. So you try to essentially devise a quantum dot. So quantum dots are small systems. So they are basically thought of as zero-dimensional system. That's why they are called dot. But they have large number of states. okay, in the quantum dot. And so that there is no sense of locality because everything is connected to everything, and so that's like a more reasonable model for this. Okay, and so one of the sort of best realization of this, which I mean people have already sort of tried to claim to realize in graphene, is this realization which is proposed by Marcel Franz and others. So it's actually quite beautiful idea, I must say. So this is realized in a graphene flake. So what is a graphene flake? So graphene, of course, you know, is a crystal of this 2D sheet. But let's say you somehow cut one small part, some 100 nanometer part of that graphene. So then it will be called a flake, right? So that's the graphene flake. Now, how do you realize? So why do you need graphene flake, and why? I mean, what is special about this? So the first thing is that you want to get a model where there is no quadratic term. So now in condensed matter, we know a very robust example of that, which are called Landau levels, right? Because Landau levels are exactly these flat bands. So and also they have massive degeneracy, right? Because just having flat bands is not enough. You need extensive number of states in that band, right? So Landau levels are originally like that. So for example, graphene has this relativistic Dirac-Landau level, and it has also this degeneracy, which is determined by the area of the sample and the magnetic field, right? Which is basically the number of fluxes through this. So now, but of course, to get SYK model, you have to have some disorder, right? So as soon as you put disorder, generally these Landau levels will get broadened, and then they will no longer remain flat, right? So how can you keep them still flat? So here there is a nice beautiful theorem by Aharonov-Kashar, which is essentially some Atiyah-Singer index theorem, which tells that if you have, so graphene has at least zeroth level, meaning that nearest neighbor hopping. Graphene has this symmetry, which is a chiral symmetry, okay, which is basically it has two sublattices, and you can just exchange the sublattices, or in other words, you can just do a transformation, and the Hamiltonian just goes to minus of it, okay. And it turns out because of this, what you can show is that if your disorder or whatever you have, it doesn't break this symmetry, then you will still have the zero mode or the zeroth Landau level preserved with the degeneracy. Okay, the zeroth Landau level will still have this massive degeneracy. All other Landau levels will split, but the zeroth Landau level, which is like a zero mode, will still have this massive degeneracy. Okay, so that's why. So what you do here, you think about a graphene flake with a irregular boundary. So if you have a graphene flake with a irregular boundary, because you have just number of atoms missing, not like a on-site potential disorder, it doesn't break this symmetry. Okay, it still has a symmetry. Now this flake could not be very large, because if it is very large, then this boundary will not affect the bulk state, whether you want a quantum dot in the bulk. Okay, so you cannot have very large graphene flake, sufficiently large so that you have large N, sufficiently small so that you don't go away from this all-to-all connectivity, right? So that you can manage, and this is sort of the numerical result. So if you put a graphene flake in a magnetic field, so this is basically showing the Aharonov-Kashar theorem, which is showing that, so this is the zeroth Landau level, so and this is as a function of flux, the magnetic field. So if you increase the magnetic field, this large N increases. Okay, so as you can see that as I am increasing this flux, more and more levels are coming and joining and becoming degenerate, and it's essentially controlled by the, so the large N is controlled by the flux of the system, number of flux quanta. Okay, so this is of course the non-interacting part, but what you can do, you can take the non-interacting part, you project into this lowest Landau level basis. Okay, so of course you will have some Coulomb energy in the system. If you project into the lowest Landau level basis, it will look like a SYK model, okay, and this doesn't have any quadratic term because it is flat. So this is your realization of the SYK model, and you can actually try to check how close it is to this ideal SYK model, which is a Gaussian random coupling. It turns out that it's not exactly this, because this is sort of the distribution of this Jij that you can calculate, which is not exactly random Gaussian. However, you can see that the entropy is pretty close. If you compare with the SYK model entropy with this graphene flake entropy calculated the way I mentioned, then it is pretty close. Okay, and it turns out that when you try to do measurement of this model, you have to also connect with leads, and this actually requires the model that I mentioned, because you have to still protect the SYK when you connect the leads. And it turns out that this M that I mentioned is controlled by the number of channels in the leads. Okay, and so you can realize this model, which is done by again Marcel Franz and others, the model that we wrote, and then they showed that you can actually realize this non-Fermi liquid to Fermi liquid transition. This is a theoretical calculation. So it will come in terms of a jump in the conductance, okay, of this dot. Okay, so basically you can realize this, and in fact there is a claim. Claim meaning they have some evidence of trying to realize this graphene quantum dot in some quantum Hall regime, and then they claim a group by the group of Philip Kim. They essentially try to show that you get this SYK type evidence. Okay. It's still not, so it clears that in this model you still have this quadratic hopping term, you have not gotten rid of it completely. But at finite temperature, sort of above the Fermi liquid coherence temperature, you seems to still see some of the non-Fermi liquid behavior. Okay, so you are going close to this, realizing this limit. There are several other proposals, some of which you can even measure OTOs in cold atomic systems. Okay, so with that I'll just stop.
How close do you, how big can n become given the two constraints?
Yeah, so you can have 100 n equal to 100. Yeah.
At some big magnetic field.
So with 10 to 15 Tesla, if you have like sort of 100 nanometer flake, then you can get n equal to 100. Inter what? Which model? No, this is just a proposal. So this model we are assuming that there are no TIJs, right? So experimentally, so of course once you realize this graphene plate, then inside there is no TIJ. Then you couple the lead, then there will be some kind of TIJs, but that is with the lead fermions. So these lead fermions are these psi fermions. Okay, but what we showed that the lead fermions will not destroy the SYK phase immediately. No. So saddle point calculation is for any energy. Okay, so it's not restricted to low energy. So then once you write the saddle point, you try to do a solution at low energies. Where the low energy approximation comes. That is because I neglected that omega term. Remember? So when I derived this, I said that there is a reparameterization symmetry, that is assuming omega terms neglected. Then I assume a Pawel law solution, and I solve it also using only the without taking the omega term. Okay. Yeah. Particle hole asymmetry, yes. Yeah, it's related to mu. Okay, I probably went over Q quickly. I don't want to go back so far back, but yeah. So as I showed that there is a relation between mu and theta. Okay, so so mu t is dependent on theta. So what you are doing is you are relating n to theta, and theta is related to mu. Then you are relating to n is related to mu. That is of course already known from UV, right? Yeah. Yes. No. So see, the thing is what they are, okay, I didn't discuss this. What they are trying to show that most of the wave functions are actually localized in the bulk. Okay. So there are some very small number of wave functions which are on the boundary. So in this model, you want to realize wave functions which are localized inside the system, not at the boundary. Okay. Yeah. No, that answer numerically also you have to take. It's not based on, it's later very sort of confirm or not confirm, later sort of justified by numerical calculation, like exact diagonalization. No, that I tried to. So here you have some guess because of this reparameterization invariance, right? So I mean you have to guess it, right? So here there are some educated guess. Yeah, that's all. In general, you don't know how to solve it. Of course. Yeah, I mean you have to numerically solve it, but yeah, yeah. Yeah, pi by 4 was a limit of theta because this has to be imaginary part of g has to be less than 0. So theta has to lie between pi by 4 and pi by 4. That's why this pi by 4 has been taken separately. I mean, so that theta goes from this, right? So that you can see from the analytical property of the Green's function. Yeah, sorry, Sandip. Yeah.
I wanted to ask you a slightly vague question, but we can discuss more
Sure.
at lunch. Which is, one way to just argue that you might get time reparameterization variance at low energies is you just start, say, if you start with the Lagrangian, you have, say, psi I dt psi.
Right, and then you, right.
Now, if the dt term is going to become irrelevant, then you'll get time.
Right.
Now, you said that if you expect Fermi, non-Fermi liquid behavior, that omega term should be subdominant compared to power.
Right.
So does that suggest that generically non-Fermi liquids will have a Schwarzian-like dynamics?
No. Yeah, okay. I understand your question. Yeah. No, so I think, yeah, so it's a good question. Actually, I have not thought about this. No, so of course, no, okay. I mean, but there could be other terms which doesn't allow this Schwarzian, right? I mean, you are just comparing that term is not there, but there. I mean, generally in standard models there will be many other terms which will violate this, right? Even Hubbard model, I think you will not get, right, because the interaction terms itself will not give this because it requires this particular form of the self energy, right? So that is important because it's not only the self consistency condition, you have to take both Swinger Dyson and the self energy condition, right, which will not be there for general models, right? Yeah.
So it's not, you can't think of it as a Lagrangian which has some psi.
Right. Yeah, right. More to it. Yes. Yeah, it's numerically, I mean, it's not very easy for finite system to find. I mean, people have tried, I think, I mean, I don't remember the exact details of this, but I think it's mostly inconsistent with replica symmetry breaking. So you can try to look at some kind of what are known as Edward Anderson order parameter. So some order parameter. So I mean, again, you have to assume what kind of replica symmetry is going to be broken, right? How replica symmetry is going to be broken. You have to some guess, right? So one guess is some spin glasses, some glass. So then you know some kind of order parameter for that. So you try to look for those type of order parameters, right? I mean, you can try to even look at the Green's functions, whether it has a lot of. Yeah, okay. I have to think about it. How exactly we'll look at into that, but people have done this. Yeah, that I know. Okay.
No more questions.
Yeah.
Let's thank
Thanks.
Sumilan again.